Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. In the previous lecture we have seen what the results about stability tell us, in the sense when systems are interconnected, right. So we've seen that if you want to actually extend the notion of asymptotic stability to interconnected systems, then you'd better ensure that there is no pole zero cancellation between each of those individual units, those systems, right. And one way of doing that is you convert each of those systems into their state space realizations and then combine those multiple state space realizations in a block diagram as you are used to doing for transfer functions. Only that in case of transfer functions it was simple, like you had to multiply those transfer functions or take their reciprocals and things like that. In case of state space realizations, we've seen that there are some algebraic operations, but it's not very difficult to see how different interconnected systems, when each of their state space realizations are known, what the overall state space realization of the interconnected system would be like, and then you had better take a look at this system matrix, the A matrix of the overall interconnected system, and figure out if its eigenvalues are there on the open left half plane. If the answer is a yes, then yes, your system, your interconnected system is also asymptotically stable, also known as internally stable, also termed as internally stable. We've seen all of those, and we saw that basically the difference between this BIBO stability and asymptotic stability arises from the fact that, well, you have non-zero initial conditions, and then you have some pole zero cancellations that can occur, and then if those pole zero cancellations occur for poles that are on the right half plane, right. So it's a combination of these three factors that lead you to different conclusions about the system's BIBO stability and its asymptotic stability. So from today's lecture onwards, in fact we started discussing this in the previous lecture, we shall focus on a couple of very critical properties of state space realizations. Remember, these are properties of state space realizations. What are those properties? Controllability and observability. At the very outset, let me make this statement: it makes no sense whatsoever to talk about controllability and observability of a transfer function. It is meaningless. The notions of controllability and observability only start to make sense once you have a state space realization in front of you. You look at the system matrix A, B, C, and if the matrix D exists, then also D, and controllability and observability will be determined by this ABC triplet, okay. So it has nothing to do with the transfer function, but the state space realization of the transfer function is what can be controllable or uncontrollable, observable or unobservable. So that's one of the things I wanted to get out of the way, because it's a common notion that sometimes people get into a twist around. So we'd better have that notion cleared at least. Apart from that, in the previous lecture we also introduced these notions of observability and controllability and motivated them, at least insofar as the solution of an initial value problem for a constant coefficient ODE, a linear ODE, is concerned. We've seen that if you want to set up your analog computer to solve for an ODE given a particular initial condition, then you need to have these two properties, observability and controllability. Why is observability necessary? Observability is necessary because in the ODE you shall be given the initial conditions in terms of y, y dot, y double dot, so on and so forth at the initial instant, that is 0 minus, okay. On the other hand, in order to implement this on the analog computer, you have to actually give some initial values to these integrators that are sitting inside this op amp or inside this analog computer. Now, how do you determine what those initial conditions of those integrators are going to be corresponding to a particular set of y, y dot, y double dot, y triple dot, so on at a given instant of time? Yeah, I mean, if you can do that, then the system is said to be observable. Okay, so this is basically the idea of observability from the point of view of a initial value problem. It turns out that there is more to it. Okay, so we have not really gotten into the nitty-gritties, the mathematical details of these, but there is more to observability than just being able to determine the initial condition. You see, if you know about the output at any given instant in time, right, then not just at t is equal to 0, then if you can also infer about the states at that instant of time, then you can actually keep solving for this system, right, because you know your ABC matrices, right, you can keep propagating this with that as your initial condition, you can keep propagating. So it is not just about the initial value problem, it is about at any given instant of time, if you know your output values, and from that if you can also back calculate or get back the values of the states of the system which are sitting within, yeah, if there is a way to compute that, then you can have a parallel simulation running where you feed those initial conditions to your this simulation setup, right, and you keep propagating this, and what you get there is going to be identical. The values of the states of this simulated system will be identical to the actual system. Why? Because you know the ABC matrices, so in your simulation you will feed exactly the same ABC matrices. What I am saying is basically, if you have the actual system, yeah, you have its output, here is its input, and sitting within the system somewhere is the state vector, right. Now somehow if you can rip it out based on this information, this is known to you, yeah, and suppose can it be determined from y? That is the fundamental observability question. So if it can be determined from this y, then what you can do is you can feed this x information, yeah, to another parallel system which is a simulated version of that original system. So this is the simulated system, yeah. So apart from providing it with this, so this is the state information that you provide it with along with the input, and then if this is your y hat, right, so you provide the same input as this given here in the same channel, yeah, and then you will see that you will notice that if this is done, if this is doable, right, if you can actually get the exact information about the state of the actual system in your simulated system, if you feed that information here through this channel, suppose there is a channel to feed it in, because after all this is a computer, right, it is a simulation platform, then what you will get here at y hat is going to be identical to y, right. So it turns out later on we shall see that this is what the idea of an observer is. Of course there is a lot of sophistication there, but this property of observability is crucial. Why is it crucial? Because it is this property of observability that lets you answer this question in the affirmative, which is to say that can you determine the state information based on the available information about the output? You can only say a yes to that, yes, if it is observable, yeah. So that is the crucial bit, that is the piece in the puzzle that is missing. If it is observable, then you can actually answer this question, okay, you can actually extract the information about the state, alright. So it is not just about the initial value condition, right, it is not just about the initial value problem and being able to figure out what to feed your system with. So I want you to pay very close attention to those two subtle distinctions I have made, to those two problems. The first problem was, forget about any original system, you have a simulation platform in which you want to set up your simulation platform with these requisite initial values, but you only have access to the output value at the initial instant. So from this output value at the initial instant, can you go back and compute back this initial state value that actually is corresponding to this output value, yeah, and if you can, then you can actually keep your platform running with exactly the for that particular initial condition, you can get a solution from your simulation, from your computer simulation. The other problem is, given that an actual system is running, this is no longer an analog computer, given that an actual system is running, right, and you have this running according to the state space equation, that is x dot is equal to ax plus bu, y is equal to cx plus du. Given that such a system is running, and you have these measuring devices which are sensing for you the output y. From this y, you wonder if there is a technique to get back xt, because remember xt is something that is sitting internal to the system, within the system, it is intrinsic. You may not be able to always access this unless you rip it open, that is, you rip open the black box, which you may not be allowed to do for fear of destruction, right. So now the point is that based on this output which you can measure, can you also get a measurement or get an idea about what the state is, right. If you can get an idea about what the state is, yeah, then you can actually feed this state values to a parallel system which is now a simulated system, and you can simulate the actual system. Why is this important? There are several purposes to this. One of the practical purposes that I can think of, we will see another very important usage of this later on in the course towards the end, but at least one important use that should immediately strike you is as follows. You want to diagnose if there is any fault in a system. So suppose this is the actual physical system, right, if this is the actual physical system, and you know what its parameters are supposed to be when the system is healthy, when the system does not have a fault, right. So then if you are able to extract this information from this output itself, what the state information is, and then you feed that state information to a parallel computer simulation system, right, then you know what the ideal output is supposed to be, which is y hat, right, and you know that under ideal circumstances y hat is supposed to be equal to y. So therefore if you pass this through a comparator now, yeah, it should always be a 0. So if you say this is plus and this is minus, this y minus y hat should always be a 0. So therefore if you put some sort of a 0 detector, right, and if you find that that signal, and under ideal circumstances which should be 0, now if that signal has some non-zero value, it means that your y and y hat are deviating from one another. Now of course you are assuming that your y hat, which is a computer, is running flawlessly because it is a healthy system, it is just after all a computer circuit, but your y, which is actually coming from a plant's output, that might develop some technical snag, that might develop some faults, right. So at least for fault diagnosis and detection, this is a very important property, right. The ability to infer about the state is very important, because then you can feed that state into a parallel simulation system, right, a computer, and compare the simulated output with the actual output and see if there is any difference. If there is no difference, your system is healthy. So this can serve as a monitoring process of the system, right. So based on whatever this output is, if this output is 0, you detect it is healthy, you deduce that it is healthy. On the other hand, if this output is non-zero, then you might guess that something is amiss. Of course there are small aberrations due to noise and other such phenomena, so those things are always there, so you might want to keep some threshold around 0, but if it goes beyond a certain threshold, then you might actually say, well, I think the system has developed a snag, there is some fault going on, okay. So there are a lot of applicabilities. You might think that for the purpose of this initial value problem in this analog computer, it is an artificial problem, right, because after all I know I have measuring devices, so if I want this particular set of y, y dot, y double dot, y triple dot and so on, yeah, why not just go and directly measure. So let us just directly measure the initial conditions at the op amps, at the integrators, and see what sort, and tune them till we get the desired y, y dot, y double dot and so on, right. So you might think, since we have access to the whole circuit, we can open up that briefcase containing the analog computer, this is a meaningless problem, right. But as I have shown you here now, it is not just about the initial value problem, but also this observability, the ability to observe or lack thereof, has very serious and important implications in things which we may not have considered thus far in our course, and indeed we shall not hereafter, such as fault diagnosis, right, system monitoring, yeah. So these are important things that we have to bear in mind. So that is why I hope that at least at this point you realize that this notion of observability is indeed an important notion. So now let us launch into a little bit more technical discussions about observability, okay. So let us see, initially we are talking about this initial value problem. So what is this system? The system is run by this AXT plus BUT, of course x at t naught is equal to x0 and y is equal to CXT plus DUT. This is the general representation of the system, right. Now suppose you consider that well, you want to sort of infer about the state from the output. So how can you do that? Well, as a starting point you see y is going to be equal to Cx plus du. I am going to drop this t hereafter, okay, just to make this simple. Now you wonder what is it that is going to allow me, there is after all only one output, right, and there are n states. So how on earth are we going to ever get one, I mean from one equation, how on earth are we going to be able to solve for these n variables, right? It seems like an underdetermined system of linear equations, no? So how are we able to do this indeed, right? So that is where you see I urge you to go back one step and see what sort of information is available with you when you have this initial value problem, right, because that is going to be the key. So we are going to deal with two distinct things which are not very different after all, very subtle differences. One is this initial value problem. So we want to figure out that for a given set of initial conditions in terms of y and its derivatives, what are the initial conditions for the state, and analogously we are going to also look at if we have information about y at a given instant of time, not just necessarily at 0, yeah, can we infer about the state at that instant of time, yeah. So the second problem will be resulting directly from this first problem. So let us look at this first problem. What information do we have? So we know apparently y dot, so remember this x and all of this, these belong to r to the n. So if there are, it is an nth degree differential equation, there are n states, then we better have information about n minus 1 initial conditions, yeah. So these are given to us, so we know this. What we want to find out is, we want to evaluate x1 at 0 minus dot 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 till xn at 0 minus based on this information. That is technically what the problem is, this initial value problem. Now this immediately suggests to us that, well, this equation, the state equation directly does not give us this y dot, y double dot and so on. So let us differentiate this. Later on, by the way, we shall see that there is a more sophisticated way of doing this, which is to design an observer. We do not really, in the actual state observability problem, not the initial value problem, in the actual state observability problem, we do not go all the way to differentiate y, y dot, y double dot and so on, right, because you see that whenever you differentiate you are amplifying noise. We have talked about this earlier also when we discussed differentiators, why realizations happen using integrators and not differentiators, right, because if you have a high frequency sinusoid, right, you see that its derivative will be omega times sine omega t. If your sine omega t is your input, your derivative is omega times sine omega t. So the larger your value of omega, the higher will be your gain for the differentiator. We have also seen this from Bode plot perspective, right, that a differentiator, a 0 at the origin, implies that your magnitude plot will rise at the rate of 20 dB per decade, right. So it amplifies gains at high frequency, the differentiator. So differentiator is always discouraged. In any practical system you will always have some noise, and then differentiator will be deadly, it will go berserk, right. So therefore in actual practice we do not differentiate y, rather we design an observer. We will come to that all in good time, but for now if you allow me this relaxation, that you allow me to take this differentiation, what is this going to be? This is going to be Cx dot plus d u dot, yeah. So then this is going to be C times Ax plus Bu plus d u dot. So here I am going to just, it is not a big deal really, I can keep this u dot and keep piling all of these, but just for simplicity's sake, yeah, I mean, and you shall see later that it is really not a big deal. I can always keep carrying on with this d as non-zero, but I will for now assume that d is equal to 0, yeah, just to simplify my calculation, otherwise it takes a pretty nasty form, right. So I will just assume that d is equal to 0, it does not really matter, nothing else changes if you consider d is equal to non-zero. I will get this as c times, so let us consider this to be 0 now for the time being, alright. So then we have this again c a x dot plus b u dot c b u dot, yeah, like this. So I will not consider the d, actually I can also consider the d, okay, let me keep the let me stay put with the d, yeah. It really would not matter much. But now let me go to the next slide. Now I am going to again substitute back this, so you will see that y double dot is going to be this x dot I am going to replace with ax plus bu, okay. So you will immediately begin to see the pattern that emerges. Let me see, c, yeah, there is this a here, and I am going to replace this with ax plus bu, yeah, plus cbu dot, right, is it cbu dot? Okay, sorry about that, I think I messed that up a bit, the c should not be here, yeah, the c should not be here, right, yeah, it is just this ax plus bu, so you take its derivative, so it is ax dot plus bu dot, yeah, so it is cbu dot, right, plus cbu dot plus d u double dot, yeah, likewise I can keep differentiating. So if you see, if I write that down in a nice little fashion, I will basically have this y dot till the n minus 1th derivative. Why am I taking only till n minus 1? Because remember my initial condition has been given in terms of the first n minus 1 derivatives, right. So I want to eventually get the general expression at any time t, so let me put back that t again, put the t back where it belongs, yeah. And then this is very interesting, what we will see here is, if you look at what is coming with x, so we have this x1 t, x2 t dot 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 till xn t, you will see that what comes here is this matrix that is like this C. So you see yt is equal to cx, yeah, y dot t, if you take the look at the second derivative, you will see it's cax, right. So I will get rid of this because I did not assume this to be 0, huh? So let me not simplify that, yeah. So I take back that exercise which I had given you, yeah, alright. So then this is going to be ca squared, likewise till the last one will be ca to the n minus 1, and this is the matrix which, again let me define it at this point, this is the matrix which we call the observability matrix, okay, and we will see shortly that this becomes a problem in linear algebra at the end of the day. Plus, what sort of a matrix do we have next? So you see we will have this, so CB is basically, yeah, so we will have this matrix, and you will see here we have this U, right, U dot likewise, and U, how many last derivative will be U, as many derivatives as of n, as of y. So this last derivative will be n minus 1th derivative of U, yeah. So this is going to be it. But what are the entries of this matrix going to be? If you really, let me call this a curly D, not the actual D matrix, but the curly D matrix. If you actually want to be very careful about this, then well you will see that this first entry is going to be this D, the next entry is going to be this, I think C times B, yeah, the next entry is going to be likewise till you will have last one as C a to the n minus 2 times B, yeah. So you see it matches with the, yeah, I suppose it should match with, yeah, I guess it should match, no, and then you keep shifting this. So this is going to shift once to the right, I believe, yeah, because next in the next column when you have y dot, if I look at the y dot, then you see the d is the coefficient of u dot. So all the diagonal entries will have these d's likewise, yeah, the diagonal entries will all have these d's, and I believe that these will keep rotating around, if I am not mistaken. Yeah, I believe it should be, that should be it. Yeah, so this will be like probably, yeah, I will have to just check, but anyway the point is that this D matrix, there is some matrix like this D matrix, you please, so maybe this you can take as an exercise. So now that we have carried on with this, so you see, let me look at the first fellow here, y dot is basically this D sitting with this u dot and CB, right. So we have CB, let me see if that is indeed the case, yeah. So we have this first fellow has this D, the second fellow has, yeah, I think I got it. So the second fellow will have CB times with U and D with U dot, yeah. So this will be CB times U plus DU dot, yeah. So this is going to be 0, I think, yes, I think that is what it is. So the last row will be like CB, let me check the third one, yeah, so even that exercise is taken back, yeah. So you will have CB U dot, yeah, CB U dot and what is Y double dot, yeah, so CAB times U, correct. So the third entry will be CAB times U, so you will have CAB times U plus CB times U dot plus D times, yeah, CB times U dot plus D times U double dot. So then this will be like C a to the n minus 2, right, let me be a little neat about this, it really won't matter as we shall see later. So C a to the n minus 2 times B, likewise till the last but one fellow will be CB, yeah, and the final fellow, the diagonal entry will be D, yeah. So this is what it is going to be. So this is the D matrix, okay. Now listen, look at what I already know these values at t is equal to 0 minus. So if I plug in t is equal to 0 minus in both the sides of this expression, right. So what do you have here? At 0 minus you see this whole thing vanishes, this vanishes at t is equal to 0 minus, because remember 0 minus is when before all excitation or external input was applied, right. So that is why I said for the initial value problem, maybe for the state observability this will again begin to show up, right, but so far as the initial condition is concerned, before 0 minus this does not exist, right, the input does not exist, so its derivatives also do not exist, simple, the input is 0, yeah. So at 0 minus it turns out that I have this y dot 0 minus likewise till y n minus 1 0 minus, this is just given by this observability matrix times x 0 minus dot 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 till, sorry, this is basically the state vector, so this is x1, this is xn 0 minus, and now this is very standard, something we have been doing since we were kids, right. This is basically of the form Ax is equal to B, okay, let me not use that notation, but you know what I mean, right? This is basically a system of linear simultaneous equations, right? This side is known to me or given to me, and this is the unknown. When can I determine this? Of course, we are assuming that this is a square matrix, which will be the case if it is a seesaw system, right? Because there is only one input, one output. Look at the size of this. How many rows does this have? How many columns does this have? Remember, C belongs to R 1 cross n. So this has n columns, and how many rows are there? This is already a single row, this is also a single row. So how many such rows are there? This is n rows, right? So therefore this is an n cross n matrix. So this O, this fellow belongs to Rn times n, right? It is an n cross n matrix. So we have as many equations as the number of unknowns. When is this solvable? So this is solvable if and only if, yeah, this is solvable, I should say, for any y0 minus y dot 0 minus. So you give me any vector, yeah, you give me any vector as the initial conditions in terms of y and its derivatives, and I will be able to determine the states for you if and only if O is invertible, or if you like non-singular, or if you like in terms of the multivariable parlance, yeah, in which case it will not be a square matrix if there are multiple inputs and outputs, precisely when there are multiple outputs, that is, yeah, then you say that this is full, here is the careful important bit here, full what? Full column rank. Of course column rank is equal to row rank. So it is, if it has full column rank, which is to say that its rank is exactly equal to n. How many columns are there irrespective of the number of outputs? The number of states is n, so the number of columns is going to be n, yeah. So if it has full column rank, yeah, then this is doable, okay, right. So if this is full column rank, then we can potentially solve for this system, okay. But in general, because we are dealing with seesaw case, we will just say that we can invert this. So this is the property of observability which can be tested via rank check or checking the determinant of this observability matrix. This is not the definition of observability. Definition of observability is if you can obtain the value of the states, yeah, given the value of the output, that is observability, okay. Be very careful to distinguish between the definition of observability and a test for observability. There are several other tests, we will not go into all of them. There is also a PBH test, yeah, for observability, just like it is there for controllability. So those tests do not define the property. The definition of the property of observability is that whether you can estimate or you can obtain or evaluate the states based on the information you have about the output, whether the states can be directly computed from the output and its derivatives, yeah, that is observability. So this is of course in the context of the this initial value problem. But now let us look at the general problem. So the general problem is, well, as I said, you know, when you want to sort of use this as a fault diagnosis or detection technique, so for the general problem we had better consider all of these things, right, because for the general problem we will then not be able to say that this input and its derivatives vanish at any arbitrary instant, right. Only at t is equal to 0 minus before the application of the input they are all 0, but in general we will have this yt y dot t dot 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 till y n minus 1 t given by this observability matrix times x1 t dot 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 till xn at t plus this D matrix, not the system D matrix. I hope my handwriting distinguishes between the two of them. This is the curly D, if you like, yeah, and you have this u dot so on till u n minus 1 dot, yeah. So that is basically it. Now this problem is tantamount to saying, so let me name this capital Y, yeah, and name this is of course x. So then the problem becomes one of saying that it's, and let me name this curly u, okay. So then this problem becomes as follows, we have this observability matrix times the x1, x2, this vector. So this is my unknown, yeah. So this is my unknown, and then on the right hand side I have this y minus this curly u, of course pre-multiplied by d, okay. And now you might say that okay, the same idea holds here, right, that whether this observability matrix is invertible or not is going to tell me about whether the system is observable or not. But here there is a small catch. What is the small catch? Think about how we are getting these, I mean at a practical physical level, think how we are getting this yt, yeah. We are feeding in some initial conditions, right, we are simulating the system, we are applying this input and its derivatives, we know what its derivatives are, right, we are actually simulating a system and measuring the output. This y is known, and it is not just known, it is measured. So there is a small difference, this is known and measured, and this is going to make all the difference between this first formulation and the second. In the earlier formulation, remember, here also it was known, but this was known and this was given to me, okay. So this is like I am trying to simulate the system. So this was like an artificial sort of a problem where I have to, you tell me some bunch of initial conditions and I have to simulate the system. But here this is actually coming from an actual system, so this is measured, this is not just some arbitrary y that has been given to me, okay. Now just think about it, if you are actually simulating from an actual system, you are getting this outputs from an actual system, right, then the question of this states not being like this, not being solvable does not arise, yeah. Why? Because see, you are giving an input and that input is resulting in this output, so obviously there exists some state for which this is true, yeah. So in this case, unlike in the previous case where it is only solvable if and only if for any initial condition in terms of y dot and so on, it is only solvable if and only if this O is invertible, yeah. But now here the claim is that, and you can see this, right, a solution always exists, because after all this is coming from an actual plant, this y is actually a measured variable, measured output from a plant. So clearly, obviously there exists some values of states for which this equation must be true, this equation is kind of like identically true. So you might think, then what is the big deal about observability? You said just a while back that in order to be able to infer about this fault detection and all this, right, you need to basically be able to get the solution of this x from here, feed it into the parallel computer, yeah, and then compare between these. So if now you are saying that, well, doesn't matter what this is, but provided this u is something that you are force feeding into the system and this y is something that you are measuring at the output of the system, so naturally a solution will always exist. So then what's the big deal, right? Are we just making too much out of this problem of observability? Turns out there is something subtle that we might be missing here. Suppose this O is singular, right, suppose this O is not invertible, even then a solution exists, but what do we know about such solutions, yeah, so I am going to use a little bit of linear algebraic parlance here, but the thing is, okay, let me give you an example here. Say for instance I have this matrix, I have this system of equations x plus, we may not use x, I wonder what symbols I should use. So p plus q plus r is equal to 2 and 2p plus 2q plus 2r is equal to 4. I have the system of linear equations, right, and let us say p plus q plus 2r is equal to 8, alright. The point is, do you think that there is a solution to this system of equations? Of course there is a solution to this, right, but what is the problem with this? The solution exists but is non-unique. Why? Because apparently on the face of it I have 3 equations and 3 unknowns, but of those 3 equations 2 of them are just scaled versions of one another, they are linearly dependent. So effectively I have only 2 equations, right. So I have only these 2 equations, p plus q plus r is equal to 2 and p plus q plus 2r is equal to 8, from which I determine that r is equal to 6, yeah. So that is all I can say. Now if r is equal to 6, then p plus q is equal to minus 4, right, and now you see I have this free variables, I can say nothing more about this. So if I, whatever q I choose, depending on that I will get some p. So I have kind of like 1 degree of freedom. Now something very similar, and if you look at this in the matrix representation form, then it is 1 1 1 2 2 2 1 1 2 times p q r is equal to 2 4 8. So what can I say about this? You can clearly see that this row and this row of this matrix are dependent, right, they are scaled versions of one another. So therefore that is resulting in this sort of a situation, right. Now something exactly similar happens when this observability matrix, yeah, is non-singular, okay. The rows will be dependent on one another. If the rows are dependent on one another, then even if I know that a solution always exists, because of the fact that after all this output is coming from the output of an actual physical system to which I have applied this input u. So if I know that the solution always exists, even if I know that the solution always exists, the problem here is that the solution is not unique. So this is the catch, but it isn't unique, and that is a huge problem. Why is that a huge problem? Because even if you look at this particular problem here of fault detection, why are we trying to evaluate this state? Because we want to feed that state vector into the simulated system, but now it is just not good enough that I obtain some solution of this equation in terms of the states, right. So for example, if I get a solution that is like x1, or rather I get a solution to the system, say, so suppose x hat is equal to x1 hat dot 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 till xn hat, and x tilde is equal to x1 tilde dot 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 till xn tilde are both solutions of, let me name that equation something, let me call that equation as, I don't know, maybe call it star again, star equation, yeah. So this is a star equation. So let us say this is the solutions of this star, okay, and sorry, and x hat is not equal to x tilde, right. So if this is the case, then we are still in trouble, right. Why are we in trouble? Because then you see that there are 2 different solutions to this system, and if you now go back to this fault detection problem, you are left to wonder as to which one do you feed in here, whether you feed in x hat or x tilde. Because if you feed in x hat, remember we are assuming that the solution is unique given a particular initial condition, right. If you feed in x hat, the 2 solutions, okay, I mean, you know, if you feed in x hat you will get one solution, if you feed in x tilde you will get quite another solution, right. So then what is the catch? I mean, like, how can it be that you can still compare? Because remember, if you feed in those 2 different sorry, where was I? Yeah, here. So if you feed in those 2 different inputs, then your system simulation itself will change, right. You are giving it 2 different initial conditions, so your solution, your trajectories will all be different, right. So if your trajectories are all going to be different, then you do not actually know which is the actual solution of the system, of the original plant, that is. So if you are comparing just some, if you are giving some arbitrary input to your simulated system and you are comparing it with the plant's output and taking the difference, yeah, then you really do not know, right. The problem here is because this output does not capture, yeah, I mean when you have lost observability at a physical level, what it means is that this output does not depend on all of the states. So what is essentially happening is, if I were to explain it in a very layman's fashion, you can have this x1 tilde, x2 tilde dot 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 till xn tilde, very loosely, this is one example, is equal to say 1, 2, 3, 4 like this, 5, 6, and then let us say last one is 10, so n is equal to 10, let us say, okay. And you have x hat 1, x hat 2 like this till xn hat is equal to, let us say 1, 2, 3, 4 till 6 you have, and then 7th, 8th and 9th are 0, and then the last one is again 10, okay. And your C matrix, that is the output matrix, is going to be like 1, 1, 1, 1, 1, 1, first 6 entries are 0, the next 3 entries are, first 6 entries are 1, sorry, the next 3 entries are 0 and the final entry is again 1, yeah. Now you see that if you pass C x tilde and if you pass C x hat, yeah, you are going to get the same y. Why? Because they agree in these 1 to 7 coordinates, yeah, they do not agree in these 3 coordinates, yeah, these 3 coordinates, but those 3 coordinates are not being picked up by the output does not depend on those 3 coordinates, output does not depend on those 3 states, right. So therefore, even though you will get the same output, yeah, the same output this for x tilde and x hat, you really can never be sure as to which particular value, because these 3 are not even missing, there could be any arbitrary value. So now which initial condition or which x do you choose to sort of simulate this system or to sort of kickstart this fault detection system, right. The solution existing is not good enough. So even though you might have had a glimmer of hope that okay, maybe for the initial value problem observability is important, but at least for the general problem of determining the states from the output, I mean it's always going to be, there is always going to be a solution to this problem irrespective of whether the observability matrix is singular or not, yeah, because after all this output has been cooked up using some input and it has actually come through the original system, so therefore this always has a solution, right. I want you to understand why it always has a solution, okay, because after all this is coming through an actual system to which you have given this input u, and therefore all this u dot, they have already acted on this system likewise accordingly and suitably spat out this output y and its derivatives and all, they will all agree, right. But now we have seen that even in this case the existence of the solution is not a problem, but the uniqueness is a huge problem. So therefore even for the general problem of getting the state information from the output, yeah, this observability, this property of observability is particularly significant, yeah. So you might now wonder a question, can we, so suppose you have lost observability, so let me summarize that. Suppose O is singular, yeah. So then you might have this question, right, that okay, O is singular, but look, what we were doing was we were taking up till the n minus 1th derivative. So let me go ahead and take more derivatives till I get linearly independent equations, right. After all, you see this analogy here, we had 3 equations and 3 unknowns, but actually 2 of them turned out to be linearly dependent on one another, yeah. So therefore it reduced to actually effectively 2 equations. So if we had another equation somehow cooked up, we could have solved for this system uniquely. So can we not do something like that here, yeah. So maybe let me differentiate this once more and maybe get a larger size and discard some equation from one of these, yeah, till I get a full rank. It turns out that due to this so called Cayley-Hamilton theorem, so the question here is, can we take higher derivatives of y to compute x uniquely? Unfortunately, the answer is no, and that is because of Cayley-Hamilton theorem. You see, Cayley-Hamilton theorem says that every matrix satisfies its own characteristic equation. So A is an n cross n matrix, yeah. So the characteristic equation of A is given by Si minus A, the determinant thereof, yeah. So this is an nth degree equation, nth degree equation or a polynomial. So this is the characteristic polynomial, this is the characteristic equation, yeah. So this is an nth degree polynomial which has n roots. So therefore, if I substitute A here, I will get some A to the n, and it is a monic polynomial, as we have also probably discussed earlier, yeah. So therefore we have A some alpha 1 times A to the n minus 1 plus dot 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 till alpha n to the power and A to the power 0, which is I, yeah, likewise. So this we know is the characteristic polynomial, where of course this chi A of S is equal to S to the n plus alpha 1 S to the n minus 1 plus dot 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 till plus alpha n, yeah. This is the characteristic polynomial. So this matrix satisfies its characteristic polynomial characteristic equation. So therefore A to the n, yeah, can be written as linear combination of A to the n minus 1 minus alpha 2 A to the n minus 2 likewise, yeah, minus alpha n I. So then what about A to the n plus 1? That is nothing but A times A to the n, yeah. So that is going to be, again this A is going to appear like minus alpha 1 A to the n minus alpha 2 A to the n minus 1 dot 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 till minus alpha n A, yeah. But again here, if you notice carefully, this A to the n, I can again rewrite this, yeah, using Cayley-Hamilton theorem again. So now let me focus on this A to the n again. So this is going to be further equal to this minus alpha 1 times some factor like this, yeah, which is basically this I am going to plug in here, yeah, and then minus alpha 2. So the point is that beyond A to the power n and higher powers, yeah, so the point of this Cayley-Hamilton theorem is that A to the power n, A to the power n plus 1 dot 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 till any power of A to the power n plus k, yeah, till infinity can all be, we have already seen an application of this. Remember when we evaluated the matrix exponential using the Cayley-Hamilton theorem, can we all be expressed as a linear combination of I, A squared so on till A to the n minus 1 alone, yeah. So therefore you might wonder, like if I can extend this observability matrix, but look what you are going to get at this observability matrix is the first few rows are going to be C, Ca dot 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 till Ca to the power n minus 1. The moment you try to write this as Ca to the n, yeah, I can replace this as a sum. This is going to be C some minus alpha, what did I write here, let me see the indices, minus alpha 1 A to the n minus 1, A to the n minus 1 minus alpha 2 A to the n minus 2 likewise, right. So therefore this new row that you are now inserting is a linear combination of preceding rows. So once you have determined that this C, Ca squared likewise till Ca to the power n minus 1, this square matrix in this case, in case of CISO, once you have determined that this observability matrix is singular, no amount of remedial measures like taking higher and higher derivatives of y will ever help you recover observability. Either it is observable as observed from the first n minus 1 derivatives and the y itself, or if it fails to be observable, higher derivatives will not add any extra information. In fact, this also tells you something even more interesting. So because this y is generally smooth, right, so we can actually expand it as a Taylor series around this time t, right. So then y can be expanded as a Taylor series. So suppose you want to expand it as a Taylor series, then it will contain terms like, you know, y at t is equal to say what should I write? Okay, let me write. So y at t plus delta is equal to y at t. This is a Taylor series, so I am going to truncate it at some point. Even if I do not truncate it, you see this is going to be delta y dot t plus dot dot dot, so plus delta to the power r upon factorial r. I think that is the Taylor series, right. So likewise, so you can go up to the n minus 1th derivative of y, and if you go to the higher derivative, yeah, you will see that it will not make much sense, because all of these y dots, they are all representable in terms of this a to the n minus 1, because they will be like c, cax, ca squared x and all. So if y is generally smooth, then you can expand y in an interval, say t to t plus delta, yeah. So suppose you know y from t to t plus delta, so yeah, so this is a slightly different notion, but I want you to be able to appreciate this as well. You see that because these are all going to be not adding any extra information, yeah, so even if you know your y over an interval, yeah, and your original system happens to be unobservable, that is, this observability matrix loses rank, right, then even knowledge about the output over an interval will not help you in recovering information about the state of the system, right. So that is the important bit. So this observability is very, very crucial, okay, not just in order to be able to solve for the state or recover the state information, but also to be able to uniquely identify that what states result in that particular output, okay. Only if all the states are reflected somehow or the other in the output, right. So if you make some small change in any of the states, it is reflected at the output in some way, then you can say that, well, the system is observable and you have some hope of being able to recover the state information. Of course, not directly by this derivative method that we have described here, but of course there is a sophisticated method such as the use of an observer, right. So we will definitely talk about some special forms. One of the forms that you have seen which will always be observable, you recall that realization that we started with at the very beginning, yeah, that we drew up this bank of integrators, yeah, and called the output of every integrator as a state, right, and we went from the right to the left naming at x1, x2, x3 likewise, yeah, and then we wrote the matrix representation of that. So in the next lecture we shall see that form which is called the observer canonical form. I actually drew it at the end of the last lecture when we were just motivating this observability and controllability. So you will see that this observability matrix happens to have full rank or be invertible for that particular type of realization. So the point is, if I give you a transfer function and if you realize it using that bank of op amps like we did in the very beginning of this of our discussions on state space methods, right, if you realize it that way, then observability is going to be guaranteed. Unfortunately, not every form of state space realization is guaranteed to be observable, right. So for example, if you realize it in that observer canonical form, it will be observable, but if you realize the same system, let us say in the phase variable canonical form like we also discussed, yeah, it may or may not be observable, yeah. In fact, we will see later that this is tantamount to pole zero cancellation. If a pole zero cancellation does not happen, then any state space realization is observable. If a pole zero cancellation occurs, then not every realization is going to be observable, yeah. So we will see that relation between similarity transformation, observability and that particular so called observer canonical form. There is also another canonical form called the observability canonical form, where not only is this observability matrix of full rank, but it also turns out to be identity, yeah. We will not talk about that, yeah, that is a very easy matrix. I mean, observability is very easy to check for such a matrix, but we will see that the matrix that we will consider, from there also it is very readily observable that, or very readily it can be inferred that the observability matrix will be of full rank, yeah, that observer canonical form. So in the next lecture when we return, we shall first start with that particular realization with those banks of integrators, and we will see that if you realize it in that form, it is always going to be observable. And then a very crucial property, we shall see that if you go via the route of similarity transformation from an observable realization, then all of those forms will always be observable, right. yeah, and then once we have done that, once that is through, we shall look at the second most important property, which is a dual property to observability called controllability, yeah, and we will likewise carry on some similar discussions about it, okay. So all of that when we come back for the next lecture. Till then, take very good care.